These are help solutions for a worksheet that's called Exam 3 Practice. So this has some stuff on static equilibrium and momentum. Maybe just those two looking at it because we have a lot of rotation practice so far. So I thought we needed a little bit of extra practice on Chapter 7 and Chapter 9 kind of problems. Here is, I think these are problems from the ends of the chapters in G and Colley, so you can look up these problems if you want. Problem 11 here, 22-gram bullet traveling at 240 meters per second penetrates a 2-kilogram block of wood and emerges at 150 meters per second. If the block is stationary on a frictionless surface when hit, how fast does it move after the bullet emerges? So that sounds like a collision. An inelastic collision because, a lot of heat's going to be generated by the friction as it goes through and emerges out the other side of the block. So we would say initial is the bullet moving and the block at rest, and final is the bullet moving at the lower speed as it's exited the other side and the block moving at some unknown speed. So we would have mass of the bullet, put that in kilograms, times v initial, that's the total initial x momentum, equals mass of the bullet in kilograms times its final speed plus mass of the block, that's 2 kilograms, times v block final x, and then solve for v block final x. I guess I should look down here. I actually wrote these solutions out, so there it is. I just called it v final. These are the x. I'm calling x the direction it's going, and these are all x components I'm putting in there. 27. 2 blocks, each of mass m, are attached to the ends of a massless rod, which pivots as shown. Initially, the rod is held in the horizontal position and then released. Calculate the magnitude and direction of the net torque on the system when it's first released. So it's just sitting like this. What's the net torque with respect to this axis? The axis is going to rotate about. And in this case, just for definiteness, I'm saying let L1 be 1 meter and L2 be 2.1 meters. And let this mass that's at these two locations be 3 kilograms. And let's calculate the net torque, or the magnitude of the torque. The direction of the net torque is actually we can see this one's farther out, so it's going to tend to make it rotate clockwise. So that's the direction. The magnitude of it, well, let's call this positive direction, so we would have plus little m times g times its moment arm, which is little m times g times 2.1, minus little m times g times 1 meter. And plug in little m equals 3 kilograms and calculate that net torque. I get 32.34 newton meters in the clockwise direction. 56. A sphere of radius 34.5 centimeters and a certain mass starts from rest and rolls without slipping down a 30-degree incline that is 10 meters long. Calculate its translational and rotational speeds when it reaches the bottom. So this sounds like an energy conservation kind of problem where we would say the system is the sphere plus Earth. Gravity is internal. We could take the friction and normal forces to be external. Friction and normal forces are doing zero work, so the net work by external forces is 0, and that's equal to change in kinetic energy. That's 1/2 I omega final squared plus 1/2 m v center of mass final squared, minus the initial, which is 0, plus the change in potential energy, which is minus m times, let's see, 10 meters times the sine of 30 degrees, it looks like. Okay, now I'm going to have an equation that has both v center of mass final and omega final. So the first thing I can do is substitute in v center of mass final is equal to r omega. Then I would have an equation that only involves omega finals and solve for omega final, and then that would answer the rotational speed, and then when we went the translational speed, we could use v center of mass equals r times omega for the omega we just found to find v center of mass final. 12. Find the tension in the two chords as shown in this figure. Neglect the mass of the chords. Assume the angle is 33 degrees and the mass is 190 kilograms. So again, in this case, we have the sum of the force X components on, for example, we could say this little circle right here where these things are tied together is in static equilibrium. So let's calculate, it has some tiny little mass, whatever it is, but in any case, its mass doesn't matter because it's not moving. It's in static equilibrium. Sum of the force X components on it is 0. So that means if we take X to the right and Y up, well, let's go down here and let's see. What number is that? That's 12. Take X to the right. Sum of the force X components is T2 minus T1 times the cosine of theta. That has to be equal to 0. Sum of the force Y components on this little thing here, and that's going to be T1 times the sine of theta minus m times g, little m times g. And that's got to add to 0, right? And we take those two together. One of them allows us to solve for T1, and then we can substitute in the other one. That allows us to solve for T2. Problem 20. A uniform steel beam has a mass of 940 kilograms. It's resting half of an identical beam as shown in figure 960. What's the vertical support force at each end? In other words, this leg over here, how hard does it have to push up? This one over here, how hard does it have to push up? We're assuming those legs have negligible mass, or we're only concerned with the force on the beams. So we're going to do the sum of the forces equal to 0 along the y direction. Let's take plus y to be up, so we could call this F left and F right. So what forces do we have on the combined set of beams here? F left plus F right minus 1.5 m times g. The sum of those three has to be equal to 0. Now that has two unknowns in it, both F left and F right, so that's not enough. The other thing we got to do is sum torques equal to 0, and I'm assuming I took the left end as being my place where I sum torques, but let's go see. Yes, sum of the torques about the left end equals 0. Let's take counterclockwise to be positive. So we would have, and in this case I called F left F1 and F right F2. So we get F2 times, well, let's see, sum of the torques. F2, the one on the right, has a moment arm of L. The slab, which is the full length of the table, has a moment arm of L over 2, and it has mass capital M. The one that's only halfway out there has a moment arm of L over 4 and only has a mass of M over 2. So we add all three of those torques and set it equal to 0. The forces that are weight forces that are going down are negative torques in my convention. In any case, that allows us to solve for F2. We substitute that into the first equation. That allows us to solve for F1. All right. Problem 20. Oh, I'm sorry. Next problem here. An object, I can't read what number it is, but an object with mass 2.7 kilograms is executing simple harmonic motion. That means it's bouncing on a spring. Oh, I see. This is a problem that is from a chapter that we're not even going to cover this term. So let's forget about that second to last problem there, and we'll go on to problem 72. A gun fires a bullet vertically into a 1.4 kilogram block of wood at rest on a thin horizontal sheet. So it's like it's sitting on a piece of, newspaper or something like that, being supported there. And the bullet has a mass of 25 grams and a speed of 240 meters per second initially. It then gets embedded in the block, and the block plus the bullet rises into the air. So we're going to use conservation of conservation of momentum in that completely inelastic collision. So initially we have, if we take plus y to be up, we're going to have py total initial equals py total final. Initially we're just going to have 230 times the mass of the bullet, which is 0.025 grams. And then that's equal to the final momentum y component, which is going to be the total mass of this, which would be 1.425 kilograms. That's just adding the two masses together, times Vy final. And solve that equation for Vy final. Once we have that Vy final, that's sort of the initial state of this. And then we just do a kinematics problem that says, if I know the initial speed of the block plus bullet, and then we want to know how high it goes in the air before it turns around and starts coming back down again, we would say initial is right after the collision, final is when it's momentarily come to rest, and we could use Vy final squared equals Vy initial squared plus 2ay times delta y, where plus y is up. So Vy final is 0, Vy initial is whatever we found in that conservation momentum calculation, and ay is minus 9.8 because it's in free fall, and we can solve for delta y in that case. All right, hopefully that helped. Ignore this problem here, whatever it is. It looks like it's the second problem, 20. That is from, I think, a chapter we're not going to get to this semester because we're doing our at-home work.